So when you query an AI model today, I mean, the visual metaphor you're always presented with is a cloud.
Right. Yeah, like this ethereal, weightless thing.
Exactly. It's
Yeah.
just an algorithm floating somewhere in the digital ether.
Yeah.
You know, you type a prompt, and this flawlessly formatted answer just sort of materializes on your screen.
Almost like magic.
Right.
Yeah.
And the tech industry has, well, they've spent the last 2 decades aggressively abstracting away the physical world.
Mm-hmm.
They're conditioning you to believe that computing is basically invisible.
But if you actually look at the engineering blueprints for the facilities generating these
The
models,
physical reality is totally different.
totally, you realize the visual metaphor is a complete lie.
Yeah, it really is.
Because the physical reality of AI, it's not a weightless cloud. It is 145 psi pressurized liquid coolant.
And massive industrial infrastructure.
Right, like 50 megawatt water towers, tens of thousands of pounds of steel and silicon that are, operating just mere degrees away from a catastrophic thermal meltdown. Yeah, it's arguably the most aggressive centralization of raw electrical and thermodynamic power since, I don't know, maybe the aluminum smelting boom of the mid-20th century.
Oh, wow, really?
Yeah. The sheer density of the infrastructure required now, it's literally forcing a complete rewrite of how data centers are engineered, like from the concrete up.
And so that is exactly our mission for this deep dive. We are looking at this fascinating document from July 2026.
It's a corporate brochure.
Yeah, a technical spec sheet and architectural blueprint from Supermicro.
Mm-hmm.
And it details their data center building block solutions,
Oh.
or DCBBS.
DCBBS, yeah.
And we aren't analyzing this to just look at consumer tech or like an advertisement.
No, definitely not.
We're dissecting it as an engineering blueprint to really understand the extreme industrial physics driving this modern AI arms race.
Because if you want to know where artificial intelligence is actually heading, you can't just look at the software.
Right, you have to look at the plumbing.
Exactly. The plumbing, the power delivery, and the thermodynamics that are keeping the hardware alive.
So let's unpack this, because the foundational shift in this DCBBS architecture, it seems to be the total abandonment of the bespoke data center.
Yeah, that's the big takeaway. Historically, if you were a major tech player, building a data center was almost an artisanal process.
Artisanal, like custom made.
Yeah. You architected the floor plan yourself, you sourced compute nodes from one vendor, your networking switches from another, cooling from like a specialized facility management company.
Sounds complicated.
It was, and you'd spend, 18 months just integrating all of it.
Wow, 18 months.
Right. But that model is entirely dead now.
Because of the AI boom.
Exactly.
Yeah.
The Supermicro document outlines this fully modular, they call it a one-stop shop total solution.
Right. Compute, power, cooling, software, all of it.
Everything. Engineered as a single, indivisible building block.
Which makes sense because the document leans so heavily into reducing time to online.
Yeah, speed is everything.
And if you're building a massive AI training cluster right now, you definitely understand why that metric supersedes almost everything else. I mean, even initial capital expenditure, right?
Oh, without a doubt. The CapEx and OpEx are important, but time to market is king.
Right, because if you are racing to train a next-generation large language model, a 3-month delay in facility integration doesn't just mean you went over budget.
No, it means your competitor's model hits the market first.
Exactly. They establish the API standard, they capture the developer ecosystem.
Yeah, the opportunity cost of idle time is just staggering.
I can imagine.
Like, when you are deploying these massive 256-node clusters of high-end GPUs, the depreciating value of that silicon just sitting on a loading dock.
While you troubleshoot, like, a custom networking topology.
Yes. It's measured in the millions of dollars per week.
That is insane.
It really is. And
Right.
that is why Supermicro is so heavily pushing these pre-validated scalable units.
Right, I saw that term. Scalable units.
Instead of building a 256-node cluster by wiring together hundreds of individual servers manually, you are stamping out identical pre-configured subclusters.
Like Lego bricks.
Exactly like Lego bricks, and
Yeah.
they interconnect via this standardized, rail-optimized network topology.
Okay, let's unpack that Lego analogy a bit, or, compared to the housing industry.
Sure.
It's like we're moving from custom stick-built mansions, the traditional data centers, to these precision-engineered, prefabricated modular homes that just snap together.
That's a great way to think about it.
But, if I buy a modular home, the pieces snap together quickly, sure.
Yeah.
But if I suddenly want to move a load-bearing wall, I can't.
Right. You're locked in.
So if an enterprise locks into this hyper-standardized, scalable unit architecture, aren't they baking in like an architectural rigidity?
Mm-hmm.
Are we sacrificing custom performance just for the sake of getting it out the door faster? I mean, what if the next generation of AI workloads needs a different ratio of compute to memory bandwidth?
Well, it's a valid architectural concern, for sure, but I think it misinterprets the nature of an AI factory.
So.
You really have to decouple this from general-purpose cloud computing.
Okay.
Like a general-purpose data center runs millions of completely disparate workloads. You've got a web server running here, a database over there.
Maybe a virtual desktop running somewhere else.
Exactly. So in that case, flexibility is critical. But an AI training cluster, it's a monolith.
Right. It's just doing one thing.
Yes. It runs one single, massive, synchronous, parallel workload across tens of thousands of GPUs simultaneously.
Wow.
And in that environment, standardizing the network topology isn't a constraint. It's literally a prerequisite.
Because of latency.
Precisely. If you have custom wire lengths or varied switch hops in a custom-built cluster, you introduce these tiny microsecond latencies.
And that matters for AI training.
Immensely. Because AI training requires all nodes to constantly synchronize their weight updates.
Oh, I see.
So the entire 256-node cluster will literally halt and wait for the slowest connection in the room before it can proceed to the next cycle.
Oh, wow. So standardizing everything eliminates that straggler effect.
Exactly. Modularity equals speed, both in deployment and in actual computation.
Okay, so the precision of the workload demands absolute uniformity in the hardware.
Right.
So let's look at the actual components being stacked together, the compute muscle. What exactly is in these racks that requires such a unified building approach?
Well, looking at the configurations here, the extreme density is what jumps out. It is completely detached from traditional IT standards.
Yeah, the specs list these crazy form factors like 10U enclosures for the NVIDIA HGX B200s, 8U systems for the HGX B300s, 4U systems for AMD's MI355X. I mean, for the listener who might not know, a U is a rack unit, right?
Yeah, a rack unit. It's about 1.75 inches of vertical space in a standard server rack.
Okay, and traditionally a server was what, 1U or 2U?
Exactly. 1U or 2U was standard for years. So in a standard 42U rack, dropping in a 10U monolithic chassis means you're dedicating almost a quarter of your entire vertical space to a single piece of hardware.
That is just a massive box of processing power.
It really is. It signifies this astronomical concentration of compute. You are packing 8 or more massive, incredibly power-hungry AI accelerators into this confined volume.
And it also mentions the NVIDIA GB300 NVL72 and the Superblade architecture for the absolute highest node density.
Yeah, the transistor density on these B200 and B300 packages has reached a point where we are essentially pushing the physical limits of semiconductor manufacturing.
But all that compute muscle is useless if it's starved for data, right?
Exactly. If the GPUs are sitting around waiting for data, you're wasting millions.
Right, which brings up the storage integration. The document specifically details petascale and object storage systems.
E3S all-flash AI storage.
Yes, and this 4U 90-bay scale-out storage. And they use the term data-intensive AI workloads. This isn't just about archiving files, is it?
No, not at all. The transition entirely to NVMe solid-state architectures for AI storage is critical here.
So we aren't talking about, like, loading a data set into memory and then just computing for an hour.
No, we are talking about continuously saturating the PCIe lanes of those GPUs with training data.
Real-time feeds of high-resolution video, uncompressed audio, raw internet scrapes.
Yes, nonstop for months at a time. The storage architecture has to operate at the exact same velocity as the silicon.
Because if a processor has to wait.
If a tensor core sits idle for even a fraction of a millisecond waiting for a storage controller to retrieve data, you are bleeding efficiency.
Right.
That's why the Supermicro blueprint emphasizes those E3S form factors you mentioned.
What's special about E3S?
It allows for incredibly dense packing of these NVMe drives. It maximizes the throughput per square inch on the front panel of the server.
Ah, so the data pipe into the compute nodes is as wide as physically possible.
Exactly. You have to paint a visual of this rack. It's not a rack of many small computers anymore. It is a monolithic, unified AI brain.
Okay, so we're cramming 10U blocks of pure GPU muscle and incredibly fast storage into a rack.
Right.
Which brings up a really crucial question. I noticed the letters DLC showing up next to a lot of these configurations.
Yeah.
Like the B300 DLC2 or the 4U AMD MI35X DLC. Are we just cramming more electronics into a metal box? Or is the architecture itself forcing us to change how we handle the physics of these machines.
It's absolutely forcing a change in the physics, and that perfectly bridges into the most critical engineering challenge of modern AI.
Thermodynamics.
Thermodynamics,
Yeah.
the heat problem, the plumbing of the internet, essentially.
Right, because if you pack that much pure compute into a rack, you create an unprecedented amount of heat. You can no longer just blow air over it.
No, you physically cannot blow enough chilled air through a 10U chassis to stop the silicon from degrading. Air is fundamentally a thermal insulator.
Wow, an insulator. So it's basically useless at this scale.
Pretty much, the heat flux generated by the silicon has entirely outpaced the specific heat capacity of air. You need a circulatory system.
And that's what DLC is. Direct-to-chip liquid cooling.
Exactly. Liquid coolants, depending on their specific chemistry, can have a thermal conductivity 20 to 30 times higher than air.
20 to 30 times.
Yeah, and a heat capacity thousands of times greater by volume.
That's incredible.
But what is truly indicative of the shift in this blueprint is what they are actually liquid cooling.
It's no longer just the main processor die.
No. The document specifies cold plates capturing heat from the CPUs, the GPUs, the DIMMs, the PCIe switches, and critically, the VRMs.
Okay, that's the detail that really stands out to me. Liquid cooling, a voltage regulator module, a VRM.
Yeah.
For the listener, a VRM's sole job is to step down the power from the rack's PDU to the highly specific, stable microvoltages required by the processor.
Right.
So for the VRMs to generate so much thermal energy that they require dedicated microchannel liquid cold plates, I mean, that implies an absolutely terrifying amount of raw electrical current passing through the motherboard.
It is terrifying. You are looking at hundreds of amps of currents being delivered to a single processor socket.
Hundreds of amps, just for one socket.
Yes. And the electrical resistance of the copper traces plus the switching losses in the VRMs themselves, it creates massive localized heat.
So if you only liquid cool the GPU die, but leave the VRM to air cool,
the power delivery system would thermally throttle or just catastrophically fail before the GPU even reaches its limit.
Yeah.
The entire ecosystem inside that chassis has to be thermally managed by the fluid loop.
Okay, here's where it gets really interesting. Because now we have specialized coolant flowing through microscopic copper channels across almost every critical component on the board.
Right.
That fluid absorbs the heat and then exits the server. This is where the internal plumbing of the rack takes over.
The in-rack plumbing, yeah.
The blueprint details coolant distribution manifolds, CDMs, and these distribute and return coolant horizontally or vertically, like the DLC2 vertical setup, which saves rack space.
Exactly. They act as the main arteries and veins.
And the document mentions hose kits with a 10-bar liquid pressure tolerance.
Yes, that pressure rating is a critical engineering threshold.
10 bar. That's roughly 145 pounds per square inch, right?
Yes. For context, typical municipal water pressure in a residential home is around 40 to 60 psi.
Oh, wow.
So you are running industrial-grade pressurized fluid at more than double the pressure of your home shower, just inches away from highly sensitive, multi-million-dollar electronics.
Which requires heavy industrial hardware. The specs mention universal cam locks for facility integration and ball valves to prevent fluid evaporation or leakage during maintenance.
Right.
You are essentially building a high-performance sports car engine inside a data center rack. I mean, we're talking about manifolds and ball valves terminology you'd expect in an automotive shop, not an IT server room.
Exactly. And that rack-level system is driven by the coolant distribution unit, or CDU.
Right.
The blueprint specifies in-rack CDUs capable of removing up to 250 kilowatts of thermal energy.
250 kilowatts from one rack.
Yes. To put that into perspective, a standard non-AI data center rack might pull, I don't know, 10 to 15 kilowatts.
So we are seeing a 20-fold increase in power and heat density in a single footprint.
Exactly.
I noticed a really subtle but vital distinction in how they handle pump redundancy within these CDUs.
Oh, based on the rack standards.
Yeah. Depending on the power architecture, for EIA standard racks, they use a 2N redundant pump design.
Right.
But for OCP, the Open Compute Project standards, they use N+1 redundancy. Why the difference in failure planning based solely on the rack standard?
It comes down to how electrical power is distributed. In traditional EIA racks, you typically have A and B power feeds running to completely separate power distribution units, or PDUs.
Okay, so completely independent paths.
Right. The hardware is designed with dual power supplies, expecting those independent paths. So a 2N pump design mirrors this two completely independent systems, where one can handle 100% of the load if the other fails.
Got it. And OCP is different.
Yes, OCP racks fundamentally redesigned power delivery. They use a centralized DC bus bar running down the back of the rack.
Oh, okay.
The power supplies are pooled at a shelf level rather than in every single server.
I see.
So because the power architecture is pooled and highly efficient, the cooling architecture aligns with it using N+1.
Meaning
You have the exact number of pumps required to meet the 250 kilowatt load, plus one single additional pump as a failover.
rather than a completely duplicated secondary system.
Exactly. It reduces the mechanical footprint while still maintaining the necessary fault tolerance.
And that fault tolerance is non-negotiable. I mean, if a 250 kilowatt rack loses its fluid circulation,
Oh, it's catastrophic.
the thermal mass of the silicon is so low and the heat generation is so high that the processors will exceed their critical thermal junction temperature in, a matter of seconds.
Literally seconds. The hardware will initiate an emergency thermal shutdown instantly to prevent the silicon from physically warping or melting.
Wow.
And suddenly, your multi-million-dollar training run just crashed.
Yeah. Right. Okay, so the CDU pushes the fluid through the servers, absorbs the 250 kilowatts of heat, and then transfers it to the facility-level cooling loop, which brings us to the site infrastructure. The document mentions rear door heat exchangers, or RDHX, for hybrid air and liquid setups.
Yeah, handling up to 120 kilowatts with intelligent anti-condensation systems so you don't get moisture in the rack.
Which is terrifying.
Okay.
But for pure high-density liquid loops, they scale way up. They talk about in-row CDUs that handle 1.8 megawatts of cooling capacity.
Right. An in-row CDU is essentially a massive heat exchanger the size of a full server rack.
Just for cooling.
Just for cooling, dedicated entirely to transferring thermal energy from the secondary rack loops into the primary facility loop. It is the intermediary step between the delicate internal server plumbing and the heavy civic infrastructure outside the building.
The heavy civic infrastructure.
Yeah.
Because the terminus of that facility loop is the modular water cooling tower.
Yes.
The Supermicro document specifies these closed-loop towers that scale from 1 megawatt up to a staggering 50 megawatts of cooling capacity.
It's almost hard to visualize.
It really is. 50 megawatts? If you look at the power draw of an average home, 50 megawatts is enough to power roughly 40,000 homes.
Wow.
We are looking at thermal rejection systems on the scale of municipal power plants, dedicated entirely to venting the heat of artificial intelligence into the atmosphere.
It radically recontextualizes the physical footprint of the cloud, doesn't it?
Completely.
The cloud is actually an industrial thermal management plant, and the closed-loop design of these massive towers is really critical.
Because of water usage.
Exactly. Water consumption is becoming a massive geopolitical and environmental liability for data centers right now. Traditional evaporative cooling towers consume millions of gallons of potable water a day.
Right.
But a closed-loop system uses liquid-to-air heat exchangers to reject the heat without evaporating the primary coolant.
So it drastically reduces the facility's water usage effectiveness, or WUE.
Precisely.
Okay, but think about this. Integrating 50 megawatt cooling towers, 1.8 megawatt in-row pumps, and hundreds of 10-bar pressurized manifolds. That creates an absolute orchestration nightmare.
Oh, for sure.
You cannot manually monitor this infrastructure.
Yeah.
I mean, if you have thousands of gallons of pressurized fluid circulating over silicon, human reaction time is way too slow to prevent a catastrophe.
You're entirely right. And this is where the physical engineering necessitates advanced operational technology, or OT.
The software side.
Right. This is section 4 of our deep dive, the nervous system. The blueprint highlights a management software suite called SuperCloud Composer.
SuperCloud Composer.
Its primary function is unifying the telemetry of the silicon with the telemetry of the plumbing.
Unifying them, because historically they were separate, right?
Exactly. The IT team managed the servers, and the facilities team managed the chillers, using completely different software stacks.
I see.
But that siloed approach completely fails in a liquid-cooled AI cluster.
Because if there is a thermal event, the IT load and the physical cooling response have to be synchronized perfectly.
Down to the millisecond.
So SuperCloud Composer specifically advertises advanced leak detection, protection, and alerts. Let's look at the actual mechanics of that.
Okay.
Say a universal cam lock on a rack, manifold, fails. A microfracture develops, and this highly conductive coolant begins to leak at, say, 2.00 AM. How does the system detect and mitigate that before the rack shorts out?
Well, the physical racks are aligned with point sensors and continuous rope sensors.
Rope sensors.
Yeah, they run all along the manifolds and at the base of the chassis. These sensors operate by measuring electrical resistance. The moment conductive fluid bridges the circuit, the sensor triggers a hardware interrupt.
Oh, wow.
And SuperCloud Composer registers that fault in milliseconds.
Okay, so it detects it instantly. But what is the automated response? Does the software just send an email to the facilities guy? Or does it shut down the pump to that rack immediately?
Shutting down the pump is only half the equation, and doing it blindly would cause the compute nodes to overheat and crash instantly.
Because the heat is still there.
Exactly. So the software has to execute a perfectly timed race condition.
How does that work?
Composer communicates directly with the workload orchestrator, which is typically a Kubernetes control plane.
Go ahead.
It commands the orchestration layer to dynamically evacuate the AI workloads from the compromised physical nodes and migrate them to healthy racks.
It moves the brain mid-thought.
Exactly. And simultaneously, it instructs the intelligent ball valves on the rack's coolant distribution manifold to isolate the fluid flow.
Wow.
And it signals the rack's PDUs to gracefully power down the specific chassis to prevent electrical arcing.
That is incredible.
Right. So the software mitigates the leak, saves the hardware, and keeps the AI training run alive by routing around the damage, all without human intervention.
The software isn't just an administrative dashboard. It's a literal, autonomous life support system for a highly volatile industrial process.
It has to be.
And they layer additional abstraction over this, right? With a SuperCloud Automation Center and SuperCloud Director. This suite handles bare metal provisioning, deploying the OS, configuring the Kubernetes clusters, and setting up the InfiniBand networking fabrics required for the GPUs to communicate.
Yes, and that InfiniBand integration is vital here.
Why InfiniBand over standard Ethernet?
Well, while Ethernet is ubiquitous, InfiniBand offers the deterministic, ultra-low latency bandwidth required for remote direct memory access, or RDMA.
RDMA, right.
RDMA allows a GPU in rack 1 to directly read the memory of a GPU in rack 10, completely bypassing the CPU or the operating system stack of either machine.
Which saves time.
Huge amounts of time. But managing the routing tables and congestion control for an InfiniBand fabric across 256 nodes is incredibly complex. The software layer abstracts all that complexity away from the deployment team.
And that abstraction reaches its absolute peak at the SuperCloud Developer Console.
Ah, yes.
This features self-service provisioning and GPU as a service, or GPO-AS. To me, this reveals the true business model. This is the ultimate magic trick of the entire industry.
How so?
Well, think about the developer. The developer writing the Python code for the neural network just logs into this sleek, minimalist web interface.
Okay.
They request a cluster of 1,000 B200 GPUs. They click deploy.
And that's it?
That's it. They have absolutely zero awareness that their mouse click just commanded 1.8 megawatt pumps to spin up, forced coolant through 10-bar manifolds, and engaged the EC fans on a 50 megawatt cooling tower outside the building.
It's all hidden from them.
Right. The software serves as the ultimate translator between human intent and massive industrial physics.
It is a phenomenal feat of systems engineering, truly.
Yeah.
But designing the blueprint and writing the software is really only the theoretical phase.
Right. Actually building it is a whole other story.
Exactly. The Supermicro document outlines how they actually deploy this infrastructure globally, and it exposes what is probably the real bottleneck in the AI economy today.
Okay, let's get into that. Section 5, white glove delivery to global scale. Because we have the blueprint, the compute blocks, the liquid cooling, the software. But how does this actually get deployed into the real world for a client? The services and support section details their planning and deployment methodology, specifically mentioning L11 and L12 validation.
Right.
In traditional data center buildouts, vendors would ship parts to a site, and the on-site engineers would wrap them, cable them, and integrate them into the network.
Like a level 6 or level 10 integration, yeah.
Right. So what physical reality forces a move to L11 and L12 validation at the factory level before shipping?
Well, L11 is full rack-level validation, meaning the compute, the storage, the internal networking, and the entire liquid cooling loop are fully assembled and stress-tested as a single unit at the factory.
Okay.
And then L12 takes it to the cluster level. You are physically connecting multiple liquid-cooled racks together, establishing the InfiniBand fabric, and running synthetic AI workloads to ensure the topology is flawless.
All before the hardware ever leaves the manufacturing floor.
Exactly. You are forced to do this because the tolerances are just too tight for on-site assembly now.
I see.
If you ship the raw components to a data center in a remote location, the probability of introducing a microsecond latency flaw in the optical cabling, or like a microscopic contaminant into the coolant loop during assembly, it is near 100%.
Wow, so the complexities actually surpass the capability of field engineering.
Exactly.
You have to build the machine, prove that it breathes and processes data perfectly, and then somehow transport that fully realized organism across the globe.
Which is no small feat.
And Supermicro highlights their global expansion to do this. They specifically call out a 1.5 million square foot green computing park in San Jose, California.
Along with facilities in the Netherlands, Taiwan, and Beijing, China, to support everything from 5G to hyperscale.
To perform L12 validation on multiple 256-node liquid-cooled AI clusters simultaneously. I mean, you need a facility that resembles an aerospace manufacturing plant more than an IT assembly line.
Definitely. A 1.5 million square foot facility, which is roughly 26 football fields, by the way, is necessary simply to house the electrical substations and the primary water loops required to stress test the hardware before shipping.
That is just wild. But think about the logistics of the shipping itself.
The physical logistics.
You have a fully integrated 10U chassis loaded with high-density silicon, massive copper heat sinks, and internal fluid channels. A fully populated liquid-cooled rack can weigh well over 2,500 kilograms.
More than 5,500 pounds for a single rack.
Right. You're attempting to transport tons of incredibly fragile, highly calibrated microelectronics over global supply chains.
Managing shock and vibration tolerances the entire way.
And they offer a 4-hour on-site response time globally for support. It really sounds like Supermicro is no longer just a hardware vendor, but this massive logistics and deployment company.
That's a great point. And then that physical friction is precisely where the algorithmic acceleration of AI collides with the reality of the macroscopic world.
What do you mean?
Well, we can conceptualize more efficient neural architectures all day long. We can design silicon with billions more transistors.
Sure.
But you still have to physically manufacture the compute block. You have to test it with megawatts of power. You have to load it onto a reinforced truck, secure the water rights to cool it at the destination, and connect it to a power grid that is likely already strained to its limits.
Wow. So what does this all mean for the future of AI? Is the real bottleneck no longer the chips themselves, but the physical logistics?
I think so. It reframes the entire narrative.
Yeah.
The limiting factor to human artificial intelligence over the next decade won't be software engineering or mathematical theory.
It'll be the physics.
Exactly. The ceiling on AI capabilities will be dictated by civil engineering, fluid dynamics, and global logistics. It will literally be decided by our ability to pour enough concrete, lay enough high-voltage transmission lines, and pump enough pressurized coolant to keep the underlying silicon from physically destroying itself.
That is, wow. That is a stark reminder. We've gone from the conceptual building blocks of AI into the massive 10U compute modules, through the miles of pressurized liquid cooling manifolds, up to the software orchestrating it all, and finally to the global supply chain making it a reality.
It's a massive, massive undertaking. No matter how sophisticated the digital abstraction becomes, computing remains fundamentally, inextricably tethered to the laws of thermodynamics and physical infrastructure.
So if you are designing a data center, investing in this space, or honestly, simply using these AI tools seamlessly on your phone, keep that physical reality in mind.
Absolutely.
Next time you get that instantaneous response from a language model, picture the 1.8 megawatt cooling towers and humming water pumps making that magic trick possible.
Because the cloud is incredibly heavy, breathtakingly hot, and incredibly thirsty.
And as AI models require 10 or 100 times more compute in the coming years, we really have to wonder, will the ultimate limit to our artificial intelligence just be our physical ability to generate enough electricity and pump enough water?
It's the multi-billion-dollar question.
It really is. Well, thank you for joining us for this deep dive. It's been incredibly eye-opening. We'll see you next time.